Can you see my screen?
Yes, sir.
Okay, so in last lecture we saw two applications. One was to calculate the area, and the other one, three applications in fact: area, then mass, and the volume. Now we have some more applications, and I'll just give you the formula, and without the physical interpretation. So the formula for the first moments, first one with respect to the x variable is mx, which is given by the integral of double integral of y times the function f, and with respect to the variable y is the double integral x times f. The center of mass is given by my over m, given by x bar and y bar, where x bar is my over m and y bar is mx over m. M is already defined on slide 40. So if you go back to slide 40, M is already defined there. This is the mass, okay, which is the double integral of f over the region R. So this is center of mass, and then we have moments of inertia. About the x-axis, moments of inertia is given by this. About the y-axis, the moment of inertia is given by this. So when you write with respect to about the x-axis, you write y square here. In the same way, first moment you write about the x-axis, you write y. About the y-axis, you write x. So this is moments of inertia with respect to about the y-axis is you write x squared here, and about the line moment of inertia, instead of x-axis is also a line, y-axis is also a line. So instead of x and y-axis, if you have a line L, and let us denote R as the distance from the point xy to the line L. Okay, then moments of inertia is the integral of r square, the distance square, times the function f, the double integral of this product over the region R. And about the origin or the polar moments, the moments of inertia will be x square, the double integral of x square plus y square into f, which is basically ix plus iy. And then we have radius of gyration. Radius of gyration about x-axis is equal to rx, which is equal to square root of ix divided by m. About y-axis is denoted by ry, which is equal to square root of I by over m. And about the origin r naught is equal to I naught over m, square root of r naught over m. Okay, so let us consider one example here. So it asks you to find the first moments and the center of mass of a thin plate whose density is given by fx y is equal to x, 5x, in the region cut from the ellipsoid x square plus y square, x square plus 4y square is equal to 12 by the parabola x is equal to 4y square. So using these shapes already know what is ellipse, what is parabola, the shapes of these you already know. But using the curve tracing techniques that we saw in the beginning of this chapter, one can trace these two curves. The first one is ellipse, x square plus 4y square is equal to 12. So the blue curve is ellipse in the picture. And then you plot the parabola x is equal to 4y square, which is in red color. Again, using the technique from the curve tracing. Okay, so the region cut from the ellipse x square, the ellipse and the parabola. So the common region here is the shaded region given in the picture. The region shaded by the black color. Okay, so this is my region of integration. This is R. Now we can, the density at point xy in this region of the thin plate is 5x. So we have the density, we have the region, so we can find the moments. First moment, center of mass, we can find. So let us do it. So first moment about the x-axis is equal to, as I said, when you calculate the first moment about x-axis, you write y here and the function fxy. Okay, so you substitute this here and integrate this over the region R. Over the region R, and then you apply the Fugini theorem. Said you can find the limit of y by drawing a line parallel to y-axis. So this is a line parallel to y-axis. The entry point of this line lie on the parabola, and the exit point also lie on the parabola. But if you draw a line parallel to y-axis at this position, the entry point is on the ellipse and the exit point is on the ellipse. Right? So that means you need to divide this region into two regions, and the division will be division of this region will be done at the point of intersection, which is here the point of intersection is this one. Okay, so the region R is divided into two parts. We call this left part as R1 and the right part as R2. Okay, so when you draw a line parallel to the x-axis in the region R1, then the entry point and the exit point you can identify by solving the parabola, which is x by 4 root under plus minus 4. So this gives you the range of y. And then you take this to the right hand side. You take to the right hand side and to the left hand side. If you take to the left hand side, the line will exit the region R1. First time integrating in the region R1. So it will exit the region R1 when x is 0. And it will exit, if I take this line to the right hand side, it will exit the region R1 when x is equal to 3. So this is the point of intersection where x is equal to 3. So integral of over the range of x will be from here to here. And now we come to the second region, R2. So here we have a line parallel to x-axis, parallel to y-axis again. And the entry point now lie on the ellipse. Okay, so we solve this ellipse for the value of y, which will be y is equal to 12 minus x square divided by 4 plus minus. So limit of y will be this. This is the limit of y, and we see that if I take this blue line, if I take this blue line to the left, it will exit the region R2 when x is equal to 3. And if I take this to the right hand side, it will exit the region R2 when x is equal to this point. And this point you can calculate by taking from the ellipse by taking y is equal to 0. So if you take y is equal to 0, you have x square is equal to 12. That means x is equal to, this is positive side, so negative value we will discard. So that means x is equal to root under 12. And root under 12 means 2 root 3. Okay, so you have the limit of x from 3 to 2 root 3. Okay, and then you do this integration. This integration will come out to be 0. So the first moment about the x-axis is 0. Similarly, you can calculate the first moment about y-axis. And when you calculate about y-axis, you put x here. And this is my fx, fxy. Okay, and the integration is over the region R. So that means the splitting that we did in our last example can be used here as well. So you have this splitting and you have this splitting. And then you integrate this one by one. When you integrate this quantity with respect to y, when you find this integral, you treat x as, this is integration with respect to y. So that means you treat x as constant. And once you have this value of this integral, then you find the integral with respect to the x variable. Okay, so you finally have this. And the mass will be the double integral of the function f. So again, we do the same splitting of the region R into region R1 and R2. So here we have the splitting again, exactly the same splitting. So we have these two integrals, and after solving this integral, you get this. So that means the center of mass will be x bar y bar, where x bar is equal to my over m, which comes out to be this, and y bar is mx over m, which comes out to be 0. So this means that the center of mass is this. Okay, so we have calculated the first moment and the center of mass in this example. Any question here? So no questions, so we move further. Now consider a thin sheet of density fxy is equal to 1. Find the moment of inertia with respect to y-axis of the sheet in the region bounded by the curve y is equal to sine square x over x square, and the interval x lies between pi to 2 pi of the x-axis. Okay. So first of all, we draw the region. So we have x is varying from pi to 2 pi. So we have, let's say, pi here and 2 pi here. And y is sine square x over x square. So the plot of the sine square x over x square is this, the one given here. So this blue line is the plot of y equal to sine square x over x square. Okay, so we have this shaded region is the region of integration, and density we are given to we are given the density is one constant. That density of the plate at point xy is 1 for all xy in the shaded region. The density is uniform throughout the region. So the moment of inertia with respect to y-axis, if you, as I said, if you calculate with respect to y-axis, you write x squared and times fxy. But in our case, fxy is 1. So you have this. And now we find the range of integration using the same technique that we have done in the previous examples so far. So the range of integration will be, you can find the range of y first. So draw a line parallel to x-axis. The entry point is this, which means y is equal to 0. So you write 0 here, and the exit point of this line is lying on the curve y is equal to sine square x over x squared. So that means this is the exit point, sine square x over x squared. And then you take this to the left hand side. It will exit the region when x is equal to pi. And if you take this to the right hand side, it will exit the region when x is equal to 2 pi. So range of x is pi and 2 pi. Okay. So you have this integral, and when you solve this elementary calculation, after some elementary calculation, you get pi by 2. Okay, so that is, sorry, what is the answer? Yeah, with respect to the y-axis. Yeah, so that's fine. So you get pi by 2. Okay, so is it clear? Any question in the application part? So you remember, keep this formula in your mind, memorize this formula. This is important, otherwise you will not be able to solve the question. So memorize all the formula and be careful about the axes. When you ask about x-axis, you write y square. When you ask for y-axis, you write x square. When asked about the line, then you calculate the distance of the line, the line from the point xy, arbitrary point xy in the region of integration, and that distance you write it here. Okay, and you can go from this to this and from this to this, because the distance of the point from the distance of the xy point from the x-axis is basically y square in that way, and distance of the point xy from the y-axis is x square, square of the distance. Okay, so this center of mass, all these formulas you should memorize. This appears again. I don't know why. Okay, now let us go to changing the order of integration. Changing the order of integration, more or less we have done already in our discussion so far. But let us see some example, more examples on this to understand it in a much better way. So this example asks you to change the order of integration. So first of all, you look at what is the order in the given integral. The order is dy. Integration will happen. Integration will be performed first with respect to the variable y. Okay, and then with respect to the variable x. So when you change the order, that means we should have the integration first with respect to x and then with respect to y. Okay, so basically you have to prove, you have to identify the reason here and change the order. So f x y will remain. Okay. So how will you do this? So first of all, to do this, you identify the boundary points of the limits of the integral. So here we have the limit of y. Is lower limit of y is x tan alpha. So that means y is equal to x tan alpha. You write y is equal to x tan alpha and plot this on the graph. Tan alpha is a constant, right? Alpha, let's say alpha is some arbitrary known value. So tan alpha will be a constant. So that means y, the curve is y is equal to constant times x. Y is equal to constant times x means this is a straight line passing through origin. Okay, so you plot this straight line. So this is the line y is equal to x tan alpha. Then you take the upper limit of y. So from the upper limit of y, you get a squared. Y is equal to under root a square minus x square. So that means you square this, both the sides, 3 of y square, and bring this x square to the left hand side. So y square plus a square, x square is equal to a square. Which means this is a circle. So you plot this circle. So part of the circle is given here. This is the plot of this circle. Because we are only dealing with some parts, so the complete circle is not plotted here. So after analyzing the range of y, we go to range of x. So lower limit of x is 0. Okay. So x is 0 means y axis. So this is x is equal to 0. And upper limit of x is a cos alpha. So this is a cos alpha. So this green line is a cos alpha. So the reason of integration is this boundary region. Okay, so this is how you identify the reason of integration. Fine. So this is the first step. You consider the y limits, plot these y limits on the graph. Then you consider x limits, plot the x limit on the graph, and then identify the region bounded by these curves. That will be the region of integration. Okay, so this is the first step. Now next what you do is you have to, since you are asked to change the order, so first you look at the order. What is the order here? The order here is the integration with respect to y variable first. How do you find the range of y? You find the range of y by plotting a line parallel to x-axis. Okay, sorry, you find the range of y by plotting a line parallel to y-axis. Okay, when you change the order of integration, you change this you change this order as well. If the integration in this example, integration is performed with respect to the y variable, this is given to us, and we are asked to change the order. So that means now I have to perform the integration with respect to the x variable. So that means I have to identify the limit of x first of all. How will you find the limit of x? You find the limit of x by drawing a line parallel to the x-axis. Okay, so I draw a line parallel to x-axis here. Why is this appearing again? I do not understand. So let us draw a line parallel to x-axis. Now see the entry point. Entry point is this, where x is 0. So you write 0 here. And the exit point is this. But you also look at if I draw a line parallel to x-axis at this point. Okay, so then entry point is 0, but exit point lie on the circle. Okay, so that means I need to divide this region into two parts. So that I'll do first. I'll divide this region into two parts. So this is how I divide this region into two parts. Now, if I draw a line parallel to y-axis in the region, in this region, then the entry point is 0 and exit point is on the circle x square plus y square is equal to a square. If I draw a line parallel to x-axis in this region, entry point is 0 and exit point lie on the straight line y is equal to x tan alpha. Okay, so accordingly we do it. So in the first region, the entry point is 0 and exit point is on the circle x square plus y square is equal to a square, which means x is equal to a square minus y square under root. Okay, so that is the entry and the exit point, a square minus y square under root. And I'll not take the negative value because we are dealing in the first quadrant. X and y are both. Okay, and then you look at if I lift this line above, then what is the exit point? The exit point is this value of y. What is that value of y? The value of y when this is the value of y when x is 0. Okay, so that means I substitute x is equal to 0 in the equation of the circle. X square plus y square is equal to a square. When x is 0, you get y is equal to a. You will get plus minus a, but then we are in the first quadrant, so we just write a. So that means upper limit of x is upper limit of y is a. Now, if you take down this curve downward, then it will exit this region, this dotted black line. It will exit the dotted black line. It will go past the black line from this point onward. And this point is the point of intersection of the circle and the straight line. Okay, so that will give you the lower limit of y. So what is the intersection point of these two curves? You write the you write the value of x here. So you get x square, you get y square tan square alpha plus y square
Sir, your voice.
Sir, you are not audible.
Sir, you are not audible at all, sir.
Sir, you are not audible.
हेलो। हेलो, मैंने अभी सर से ना बात की है। सर कह रहे हैं कि उनका नेटवर्क इशू है, तो सर रीशेड्यूल कर देंगे कल क्लास। तो आप लीव कर सकते हैं सारे।
थैंक यू।
Thank you, Chirag.
Hello everyone. Can you hear me?
Yes, sir.
Yeah. So I think we joined a little bit late because that I was just having another class for the BTech third year, engineering physics, this semiconductor physics theory. So that's why it ran a little bit longer. So that's why we a little bit late. Okay. So I'm sure now yeah. Can my voice is like is it everyone can listen me properly, or somebody is saying that voice is too low?
So we can hear you clearly.
Okay. So then you can set up like probably what is your name? Kunal. So maybe you can check like whether your systems is like proper. Maybe I just had a class like last 1.5 hours. Everybody was fine. Like I think maybe you want to check your system. So okay, so I think welcome to this PHN-101 course. I'm sure that you guys have a lot of wonderful lectures on yeah. So I'm sure that you will have a lot of lectures so far on different aspects of this of your course structures and departments. So so far there was any lecture has happened on condensed matter physics or solid state physics, or I just want to know what are the things has been covered in these types of lectures. Hello. So what has been is there any lecture before on condensed matter physics or solid state physics before in the PHN-101 course?
No, sir, not yet.
So what happened? What are the things has been covered?
So we had spintonics, and then we had some atmosphere of the Earth. We had nuclear physics.
Okay.
And we had
quantum computing, sir, and then there was one about laboratories.
Okay.
That's all.
Okay. And you guys are all mainly like for engineering physics people, right? Or some other is also there?
No, sir. This is a mix of engineering physics and BSMS dual degree physics.
Okay. So both are there. Okay, good. So I am seeing that you are enjoying that your classes and this is this course when we developed this course, the primary objective of this class course was to get you introduced with the different possibilities in the engineering physics or BSMS program. This is the different opportunities our physics program offers, especially with an emphasis on the research directions and what you are going to read in more in the later on. So today I will give you a very brief overview first today on the solid state physics or semiconductor physics. So let me first share my screen, and then we'll start the discussions. Is my screen visible?
Yes, sir.
Screens are visible?
Yes.
Yes, sir.
Yes, sir.
Okay. So yeah, this is one of the very important part of our this in the engineering physics program, or for that say any engineering or physics program, is the solid state physics. So you guys will have a lot of courses later on the solid state physics. For example, there is a core course on semiconductor device physics which I teach for the third year. And then in second year also, then you guys will have some preliminary course on this thing, and there will be a lot of advanced level course on semiconducting or solid state physics things. And like any other areas, including nuclear or atmospheric or optics. Similarly, solid state physics or condensed matter physics is an area whose domain is very, very large, as you can see later on. So now it's not only about the discussions about what is a solid or what is a liquid or what is a gas. I'm sure that in your courses you guys have all know about the difference between a solid and a liquid and a gas, and you know that it is the strength of the interaction which determines that if something is a solid or something is a liquid or in something in a gas. For example, in the case of gaseous molecule, the interaction between the two molecules is very, very weak. So, but on the case of the liquid, the interaction is little bit stronger than the gas, but not strong as the solid. But in the case of solid, you have a very, very strong interaction between the neighboring molecules, and you always find a particular shape and structure of the material. Now, so the solid state physics or the condensed matter physics in a larger sense, they discuss about the solid and also some extent to the liquid and the interface between the solid and liquid. Now, all the applications including our semiconductor device, our electronics, and then this applied material science, all the areas of the material science, development of novel materials and their applications for transistors or IC chip or for any day-to-day gadgets or any power generating device. So everywhere, or light emitting solar cells, LED, all these things, whether it's a solar cell, LED, everything this falls under this area. So now, before I start a conventional discussions about this material, just I wanted to say you that this condensed matter physics, which is includes both the solid and liquid. So they are they have lots of different goals, and there are lots of things has been explored during the previous few centuries, which has led to this foundations of this condensed matter physics. The most important, which you have already maybe one of the theory which you have little bit know, that is called quantum theory. And once the quantum theory was in place, there was a significant amount of discovery has been happened in the quantum materials, which includes this there are different types of exotic materials. Then there are the graphene, and then carbon nanotube, and then maybe you have heard about the nanomaterials, which has application in almost all different fields. Along with that, there are things like superconductivity, and then energy harvesting or energy generations, battery and storage systems. Then these the new generation semiconductors. These are all area which the condensed matter physics cover that things. But this is so vast area. For example, I have given you a chart here. You can see that it is consists of the hard matter as well as the soft matter. Now, what are our hard matter? So hard matters they again can be classified into a crystalline solids and then non-crystalline solids. Okay, crystalline solids means for example, this metal. You see the copper wire in your house, which have been used for wiring, the electrical wiring. So that's an example of a metal. Okay, so that is also a crystalline solids. So that means it has a crystal structures. Similarly, this insulators, for example, wood or chalk, everything which cannot current the electricity. That is, they are the insulators. They are also example of crystalline solids. And then there are semiconductors, which is usually not that much conducting, but in certain conditions they can conduct the electricity, and this is the heart of our electronics industry. Now, I'm sure that if I ask anybody here, what is the difference between the metal, insulator, and semiconductor? Can anybody comment on that? What will be the difference between the fundamental difference between a metal and an insulator and
so existence of free electron?
In where?
So, I mean, I don't know how to explain it.
That's fine. That's fine.
But like, for example, in metals, there are existence of free electrons, which is why the electrons can move freely and hence conduct electricity. In case of insulators, there are no free electrons, so they cannot move freely in the presence of potential difference. And in semiconductors, there are certain conditions where this phenomena can be seen, but in other it cannot.
So difference between the energy gap between valence band and conduction band. So in metals it is overlapping. In semiconductor it is less. In insulator the energy gap is very high.
Yeah, very good, very good. Anybody else? Want to comment something on that? Yeah. So basically, like the major difference between these three different types of solids is comes from their band gap. So the difference between the metal and insulator or semiconductor is you can call it as a quantitative. And the difference between not quantitative, it's qualitative actually, not quantitative, it's qualitative. For example, somebody says that metal don't have any band gap or it's cross over each other. So that means we later on know that in any types of material, there are two different types of energy gap, two types of energy levels are there. One is called the valence band, which is usually completely filled by the electrons at 0 Kelvin temperature. Another is called the conduction band, which is usually empty at 0 Kelvin temperature. So this valence band is completely occupied by the electron at 0 Kelvin, and conduction band is completely empty by the electron at 0 Kelvin. So in the case of the metal, you cannot distinguish the valence band and conduction band. So they are superposing on each other. So that's why in principle, there is no band gap kind of things. Now, some people also try to talk it in a more fascinating language. So there is something called Fermi energy level. So Fermi energy level is the highest field energy level at 0 Kelvin. So in the case of the metal, there is no the so-called Fermi energy level, or it lies between the conduction band and valence band. But in semiconductor and insulator, there are this valence band and conduction band, they are separated. They are not like metal, they are superimposing on each other. In the case of the insulator, the difference between the valence band and conduction band is high, something like 6 electron volt. You know what is the definition of an electron volt, right? It is the amount of the work you need to do if you wanted to pull an electron against a 1 voltage difference, work function difference. So amount of the work you have to do, that is called the 1 electron volt. So it's a form of energy. So if the energy difference between the valence band and conduction band is somewhat like 6 electron volt or more than that, then it is very, very difficult to bring an electron from the valence band to the conduction. And what we say that when the electron is in the conduction band, that means this is in the outermost cell, then those electrons can participate in the electron conduction. So the electrons, if it is in the valence band, so they cannot participate in the conduction. But those electrons, they are in the conduction band, they will be able to participate in the carrying the current. Okay. So in the case of the insulator, it is it's not very easy to excite an electron from valence band to conduction band. Now, you can ask this question how can I get the electron from the valence band into the conduction band? So to take an electron from the valence band to the conduction band, we have to provide some energy, external energy. This external energy can be heat energy, can be magnetic energy, or it can be some light energy also. So when the electrons absorbs this energy, so then it excites from the then it goes from the valence band to the conduction band, and once it is in the conduction band, then it starts participation in the electrical conductivity. Now, for the case of insulator, it is not that much easy, like, to go the electron from the valence band to the conduction band. But for the semiconductor, although at 0 Kelvin temperature, all the electrons are in valence band and the conduction band is empty. But once it is in the room temperature, and you know that the standard room temperature is how much, to 25 degrees centigrade. I mean, you can argue that in Rajasthan it might be 30 degrees centigrade, and in somewhere else, at in hilly area, it can be 20 degrees centigrade. But in standard, it is 25 degrees centigrade, which is equal to 300 Kelvin. Now at 300 Kelvin, so if the temperature is 300 Kelvin, then the amount of the energy is given by the kB into T. Okay, so if I wanted to find out what is the temperature at a particular, what is the energy at a particular temperature, that is given by this term kB into T. So where kB is the Boltzmann constant, this is a universal constant. Okay, this is a universal constant, and this T is the temperature. This is a constant 1.38 into 10 to the power minus 27 Joule Kelvin, and T is the temperature. Now, if you consider it's a room temperature, which is 300 Kelvin, then you will have an energy of 25 milli electron volt. So this much amount of energy is sufficient to excite an electron from the valence band to the conduction band. That's why a semiconductor at room temperature, they will start participating in the electrical conductions. So so that is the major difference between the metal insulator and semiconductor. And but nowadays there are lots of these exotic materials have been discovered. For example, you might have heard about topological insulator. Topological insulators are insulators this is basically an insulator, but the top layer is insulator, just below layer is conductive, is semiconductor. So how come it's possible? So that will later on you will learn how that is possible. But there are also material exists which behaves insulating from in the top surface layer, but in the below layer the electrons are can carry the current. So it's a very good system. You can make a very good insulated wire where you will not get any electrical shock, but you will get a very highly conductive electrical conductions between the wire. So you don't need to encapsulate the copper wire with some plastics or something which we have to do for normal wiring. So this is different types of materials are there, but usually the semiconductor material which have a band gap from somewhat you can say that 0.5 electron volt to all the way to 3.5 or 4 electron volt. For example, the standard material silicon, which have been used for semiconductor industry, whether your cell phone or your your laptop, it is made out of the amorphous silicon IC chip, and that has a band gap of 1.1 electron volt. And you take another semiconductor which is commonly used, germanium, 0.7 electron volt. And then there are some large band gap semiconductor is there. For example, titanium dioxide, which is used in the paint and in the toothbrush. Okay, so in the toothpaste and also in the paint industry and also different medicine industry, this titanium dioxide powder is used. It has a band gap of 3.2 electron volt. Similarly, there have been this zinc oxide, aluminum oxide, there are lots of metal oxides is there which have a little bit larger band gap. But these are all semiconductor. But so this is where we can distinguish the crystalline solids, and then there are non-crystalline solids, amorphous material. There is no long-range order in this material. For example, you can take a chalk. If you break a chalk, you will get a powder, but there is no crystallinity in this chalk. It's like an amorphous material. If you take one particular unit of this chalk, you will see that there is no crystallinity or no symmetry in any particular direction. Now, these crystalline solids, they are also there are different types of things exist in a crystalline solids. One of the important things which define the quality of a solid is called the defects. For example, you have seen all these electronic gadgets, right? All these your cell phones, millions of cell phones, millions of laptops, computers. They're all made from the silicon, let's say silicon IC chip. But how does they are made out of actually? So there's a standard manufacturing technique to make this or to grow these crystals. But when you grow the crystal, so during that process, you incorporate lots of defect states or lots of impurity in the systems. Now there are different types of defect states is there. For example, there are point defect states, there are dislocations, there are surface defect states, there are interfaces. So these are very, very important. Now, depending upon which applications you are looking for, you have to minimize the defect states. And there are lots of people who are studying on these defect properties of the material. Now, this non-crystalline solids or the amorphous solids, they can be three different types. One is called the quasi-crystals, which behaves like a crystal, but it's actually not a crystal. And then there is a very, very important example is called the polymer. For example, like, all the, plastic water bottle, you are drinking Coke or like Pepsi from the plastic bottle. They are all example of the polymer. They are made of like, some kind of polycarbonate material, like cross-linked polycarbonate material, which is nothing but a polymer, which is a non-crystalline solids, large gigantic organic molecules. And then there are this glass, amorphous solids. One very important example is the glass. I mean, in glass, you know that this has been used in everywhere, whether it is in building or like, in different industry, like, glass is there. And there is a severe puzzle among the people, like, what happens to the glass. And when, like, let's say you heat a piece of salt, you can always melt that salt and you call it as a phase transformation. But what happens when you heat a glass? So whether it will be a liquid glass or like, whether it will be still like some viscous glass. So it is called glassy transition. So there are like, a huge number of people who are studying on that by using statistical mechanics. So similarly, like, another class of material is like, this condensed matter system is the soft matter, which is like, also called biologically inspired materials also. Now the soft material, like, this has been used for the soft material electronics, for example, organic electronics or hybrid material electronics. One of the major example of the soft matter is colloidal dispersion. All the like, different types of medicine which you take, they are an example of a soft matter. They are colloidal dispersions, right? The first colloidal dispersons you probably have known about is the milk. That is also a colloidal dispersion. And experimentally, which you have seen that you have studied that if you took a pollen grain and put it in the water, so like, you can find out how does the Brownian motion happens in a colloidal dispersons. And you can always use this Einstein's divide theory to explain this kind of motion. Then there is another example of this soft matter is called the liquid crystal. And this has been like, very popular for some time. Almost all of your house nowadays has the LED TV, like, before the LED, there was the LCD display was there. LCD TV was there. I mean, the CRT or the cathode ray TV was this old TV. If somebody have like, very, very old, this square type of black and white television, like, you can ask your grandfather or grandmother, they might have seen that kind of things. But most of like, in our previous generation, they have this LCD or liquid crystal display. And still nowadays it is extensively used. I mean, nowadays we all have this LED TV, like, because the production of the LED cost has been reduced significantly thanks to the development of this condensed matter system research. But this liquid crystal display or LCD display, still you can see in many places, whether you go to the train line, like, all the like where the train's names, like arrival, departure has been displayed, or if you go to the airplane, like, so there everywhere the display, wherever you see the display, there the LCD display. Okay. And then now, nowadays, of course, you have the LED screen and TFT screen, like, so that has like, that have been an advancement over this thing. And then there are these polymers, mates and solutions. And finally, there are the biomaterials. See, this is, you might be thinking this is an area where bioscience and biotechnology deals with, but it is not actually. All the proteins, membranes, nucleic acid, their structure evolutions. So that is also falls under the soft condensed matter physics. So you can see that, like, the domain of this condensed matter physics is so vast. I just only differentiated the different materials as per their properties only, like, how does they look like, but I have not talked anything about their application yet. So this is all about like, very large dome of condensed matter physics, and each and everyone just pick up one particular dome and work on that particular area. Now, like, you all have heard that, like, there are the Stone Age was there, Bronze Age was there, then there was the Iron Age was there, and now we have this nanotechnology age. Now, to the discovery of the quantum mechanics, now we can possibly, like, manipulate the materials properties in the nanomaterials case. Yes, Kunal sir, Any question? Hello? Kunal, you have some question? Or no? I saw your hand raising, so that's why. So now, I mean, we have heard about the nano, what is the nanomaterial? I mean, anybody can tell what is a nanomaterial? We know about macromaterial. Like macromaterials means the materials which has a length scale of meter, centimeter, or millimeter. All the thermodynamics, hydrodynamics, and elasticity things that comes under the macro domains. And then we have the micro, quantum mechanics, many body particles things. And then in the micro domain, there's a one important term so you all talk about is the nanomaterials and angstroms. Now, anybody can tell me what is one
in terms of meters?
Yes.
So in terms of meters, I believe it's 10 to the power -9. If I remember correctly.
Yes, 10 to the power -9 meter. So he said that 10 to the power -9 meter. So you can see that this is a very, very small length. You have seen your meter scale. You know how does a 1 meter looks like. So if I have to divide the 1 meter by 10 to the power 9, so you just have to put 9 zeros after 10, and then if you have to divide number 1 by that number of 10 to the power 9, so then you will get 1 nanometer. So you can think about what is the smallness we are talking about here, right? So I'll just give a very typical example, you are not in the campus, so you cannot get it. So basically, if you just start wherever you are, let's say if you from that place, if you start walking to the nearest market, and then the distance you travel, and on the other hand, if you start from here and just walk straight to the America, then how much distance you will travel? If you take a ratio, that is 1 nanometer. So it's so the point is that it is very, very small. Our here is micron scale. So this is nanometer region. And the most important question is that how can we handle the properties of the material in this scale? I have a piece of chalk in my hand. If I throw that chalk, I know where the chalk will go. If I have a ball in my hand, if I throw that, I know where that ball will go. Because I know the initial velocity, I know the final velocity, I know the time which have been spent, so I can find out easily the distance by using the kinematical equations. But let's say I have a nano chalk, which is 10 to the power -9 meter. And if I say that I throw that chalk with 10 Newton force, how much distance it will travel? Now, first of all, you will ask, this question is an absurd question because you cannot apply 10 Newton force on 10 to the power -9 meter object. We are talking about a very, very minute object. So we can't apply that much amount of force. And even if we are able to apply that much amount of force for the sake of argument, we can't apply this F is equal to ma or S is equal to ut plus half ft square, all these kinematical equations to solve this problem. Because these nanomaterials or these subatomic particles, they don't follow the classical Newton's theory. They follow the quantum mechanical theory. So that's a completely different theory. That's a completely different concept. So then we cannot apply those theories there. So we have to inculcate a completely new physics, a new mathematics, a new science to explain the behavior of that smaller particle. And that's what the quantum mechanics talked about. Quantum mechanics deals with these subatomic particles and their behavior. And now you know that if I have to design an IC chip, whatever there inside the motherboard of your laptop is nothing but an IC chip. And what is the IC chip? There's a millions of electronic circuit. And each of the circuit has a dimension of few nanometers. So now somebody has to make it and somebody has to know the properties of the material at that scale and optimize the properties. Then only they will be able to make a larger amount of panel and finally a device. So that's why it's a completely different region. For here, you can see that here there's a picture of a bull which have been taken. It's the length is 2 micron and it has been taken by a microscope. So obviously the normal microscope, optical microscope, which you have used in your class 12 biology experiment to see the blood. If you have done but I don't know whether you have done it because there was the schools were closed for a long time. So but that can see only a very, very larger distance, like millimeter or something, even 10, 20, 100 microns. But you can't see a nanometer. But nowadays, there are very, very powerful microscope is there. For example, the electron microscope, where you can see also like these nanoparticles. You can see one atom. Like if I have like a gold atom, so I can see each and individual atom of a gold. I can see each and individual atoms of a graphene, carbon. So that much is possible, like, I mean, so like, the power of something is seeing there's something. So you can also see this, the motion of these systems, the motion of the electrons, so the motion of the atom. So that's much powerful things has been happened in the progress of this nanomaterials design. And because of that, this technology has an application in almost every area. You talk it about the electronics, you talk about the optics, photonics, you talk about like, material science, any branch of engineering. And like, including like space technology, including the medicine technology, everywhere it has the applications. So, so I'll just like, I mean, today, like, mainly since talking about the nanophysics and low dimensional physics, like, so the first thing is that that this 1980 that IBM Watson research laboratories, people have find that the very small purity samples do not obey Ohm's law. So this was the first discovery when people have seen that Ohm's law is not always valid. We know that V is equal to IR. If I supply a voltage in a wire, there will be a current, and how much current it will be determined by the resistance, right? And also the shape of that, the geometry of that wire, right? This comes in the resistivity term. But there are systems like where people have found that it does not obey, like I mean this laws of this Ohm, and that has been first found in this IBM Watson lab. So for example, like, I mean, so this led to the rapid development of the study of materials on a microscopic, nanoscopic scale and the study of materials at lower dimensions. And what we have done for that, today we have this integral and fractional Hall quantum effect, two-dimensional electron gas. So maybe you have heard about the Hall effect. In Hall effect, what we do, we apply a magnetic field in a perpendicular direction to electric field, and we measure the current in the material. From there, we can find out what is the carrier concentration in the material, what is the polarity of the material. That is called Hall effect. But today we have a quantum Hall effect. Not only that, we have a fractional quantum Hall effect. That gives to the exotic phenomena and exotic material properties. Today we have a single electron transistor, which made it possible the quantum computations and also the quantum cryptography. And also, like, I mean, we have this quantum dot, which are the nanomaterials, which are the size of 10 nanometer or smaller than that. Today, we can make the artificial atoms and like, different types of new organic materials we can make. For example, these buckyballs or carbon-60, carbon nanotubes, graphene. And this has actually revolutionized the field of the material science. And this is all possible because now we know what happens by this using the laws of quantum mechanics, what happens at the nanoscale, and we know that how to tune the properties of the material in the nanoscale. And we can manufacture the materials in the nanoscale also. Now, in this regard, I will just tell you about some interesting phenomena. Like, for example, like, if I have to measure the temperature of something, like another interesting phenomena, like, I mean, which will be in this case, is that if you want to know the temperature of something, like, you use a thermometer. For example, you see there's a thermometer here. This is 300 Kelvin, this is 200 Kelvin. I am going to lower temperature. This is a very important number. Very often you have to encounter this number. The temperature of liquid nitrogen is 77 Kelvin. When you do the low temperature, the further cool you down, like, you do that at 4.2 Kelvin. That is called liquid helium. So this is the, like, 4.2 Kelvin. But what happens if we go to 0 Kelvin? Like, let's say I have a piece of sodium and I am cooling it from 300 Kelvin. Okay, I can, by using liquid nitrogen, I can cool it to 77 Kelvin. By liquid helium, I can cool it 4.2 Kelvin. But what will happen if I go to the 0 Kelvin? This is not possible. Like, I mean, the thing is that was once you go below, like, 2 Kelvin, then things become extremely, extremely complicated. And for more than 100 years, people are trying, like, their best to cool the material below, like, 0 Kelvin or near about 0 Kelvin. Now, we have all read this Boyle's and Charles law, right, in our textbook earlier. And if you make together the Boyle's and Charles law, you have the ideal gas equations. Now, according to the Boyle's and Charles law, I mean, if you wanted to bring a material towards the 0 Kelvin, a liquid will not be a liquid will not be a liquid. It will start to form in some other temperature. And experimentally, it was not possible also to go to that much close temperature. Now, I mean, even if you take a gas, if you bring it towards the 0 Kelvin, it will become liquid. And the Boyle's law is not valid for 0 Kelvin temperature, not valid for a liquid systems. So that's why the 0 Kelvin sometimes is called the lowest temperature in the universe. It's called absolute zero. But now, because of the discovery of the solid state physics, people are now able to go to temperature very, very close to 0 Kelvin, 1/60,000 of the 0 Kelvin. And you know that this was based on the discovery of an Indian scientist, Satyendranath Bose. And he has discovered this Bose theory, this Bose-Einstein statistics and Bose theory or Bose-Einstein condensation. Based on that, people have been able to reach now a temperature near about 0 Kelvin. And when the system goes to 0 Kelvin, then it started behaving completely different way. Not like a solid, not like a liquid, not like a gas. Any one of these condensed matter form. It's like a completely different form. Now earlier people have seen the plasma, which is the energized state of matter. Which is the energized state of matter, where the solid and liquid states are together. And sometimes people call that plasma state is a fourth state of the material. And now when people are able to reach the temperature towards the 0 Kelvin, they found that completely different things happen. All the atoms, they got locked in a zero momentum state. And that state, they call it as the fifth state of material. So apart from solid, liquid, gas, and plasma, we have now the fifth state of material also. So that also falls under the condensed matter physics. And what will happen, once we are able to lock all the particles in one particular momentum state, we'll get a coherence in the systems. And then we'll be able to make a very beautiful laser out of that. That is called the quantum lasers, quantum coherent lasers. Quantum coherent lasers, unlike the normal lasers, these are the extremely powerful lasers, and they can carry the informations. So for example, nowadays, we carry the informations by optical wave. But now the quantum information is quantum wave, these quantum lasers, they'll be able to carry the information in a quantum bit by using this, this locked bosonic particle at 0 Kelvin. So that also falls under the quantum mechanical physics. So now the first person, who started these things is that this Kamerlingh Onnes in 1908. He was first, cooled the material to, he was able to cool the helium by 0, near the 4 Kelvin. For that, he got the Nobel Prize. From then onwards, there are, as I said, that millions of scientists, they are working, how to cool the material, because that will give you the new types of understandings of the materials. And that gives you the fifth state of material. Now, there is one more exotic things in this solid state physics, which I after nanomaterials and quantum physics, and then this, this super cooled atoms and quantum information, I'm talking about is the superconductivity. Now, you probably have heard, these things, that whatever the power has been produced in the grid, only 30% power, even less than that, 25% to 30% power comes to our household. Remaining 60 to 70% power get lost while carrying on the wire by the Joule-Hitting's law. So whenever you pass a current in a wire, so there will be heating of the system, and the systems will lose the energy. So that's why you don't get the whatever the power has been generated in the thermal power plant, you only get 20 to 30% of the total power. Everything is got lost. And that's why that is one of the reason apart from the scarcity of the fossil fuels, or this big power cut in everywhere. So now how good it will be if you think that if I have an wire where there is no loss of the power, whatever I generate at the power plant, a similar amount of power I am delivering at my target positions. Whatever I am generating at my power point, a similar amount of power I am sending it to my house. So there is no power loss. So that means when a wire carries a current, it will not able to lose any power. So it will conserve all the energy. So, but that is not possible, because we know that that all the wires, they have a resistance. Like, we have the Ohm's law, V is equal to IR. Like, whenever you have a current in a systems, apply, like, playing between the two voltages, there are resistance. And when there will be resistance, then there will be I square R. There will be a heat loss, and that heat loss is given by current square into the resistance. Now, resistance cannot be zero. If the resistance is zero, then only the power loss will be zero, because current cannot be zero. I mean, if the current is zero, then everything is zero. So only way you can have the resistance is zero. But there is no material it was found, like, that where the resistance was zero. But this in 1911, this guy, this Cavalli-Owens, while doing some experiment with mercury, what he found that, like, when the mercury goes to 4.2 Kelvin, near about 4.2 Kelvin, suddenly the resistance drops and it becomes zero. And beyond that temperature, below that temperature, the mercury flow like a resistance-less liquid. So that means, like, if something don't have any resistance, that means there is a superconductor. So that gives the concept of the superconductivity. So superconductors are materials, like, where the current can flow without feeling any resistance. And more interestingly, it has been found that these materials are actually diamagnetic. That means they exclude the magnetic fields from inside them. But the temperature at which the transition happens from the normal material to the superconducting material, that is important. According to the Cavalli-Owens discovery, it is at 4.2 Kelvin temperature. But you know that 4.2 Kelvin is too low. We are living at 300 Kelvin or 300 plus Kelvin. So I have to design a wire at 300 Kelvin or 300 plus Kelvin. 4.2 Kelvin के wire में कोई फायदा नहीं है. But at least this was a breakthrough, like, invention or breakthrough concept, which leads us, like, to the direction. Now it is possible by optimizing the material properties to increase the temperature to tune the superconducting phase transitions. And thanks to, like, all this discovery, now there are materials which have been discovered, especially the copper-based compound, where it is possible, like, to flow the current without feeling resistance, not at room temperature, but at minus 20 degrees centigrade. And there are huge number of experiments that are going on, like, to bring the temperature transitions to the normal level. And some of them are also possible. And you can see that, like, for example, like, this, I have talked about the mercury. Another example, like, the thallium. So that, like, shows the transition at a lower temperature. This is the case of the cadmium. And you see that the case of the lead, it happens near about like 6-7 Kelvin temperature. So that means it is possible, like, where the transition can happen at a higher temperature. So this is the resistance versus temperature graph, like, according to the different scientists. So Lord Kelvin said that this is, like, this is the behavior of the semiconducting resistance with respect to temperature. Then according to this 1904 discovery, they find that there is a possible to drop the resistance below a temperature. You can see that the resistance is zero at this particular temperature. So now there is, like, a new theory has been come which allows that it is possible to have a zero resistance state in a material, and material is able to carry current, like, without feeling any resistance. And this material, they are called the superconductor. And unlike a normal material, they push the magnetic field. You know that from the Maxwell's theory, like, if you have a material like this, a spherical ball, and if you pass a magnetic field, the magnetic field will pass through the ball. So at a temperature above the critical temperature is the temperature where the superconducting transition happens. So a temperature above the critical temperature, all the magnetic flux line can pass through the material. But below that superconducting temperature, all the flux lines has been expelled from the material. So that means it's behaving like a diamagnetic material. And this effect is called the Mesenheimer effect, or Mesenheimer-Osenfeld effect. This is a very important effect which says that the material below the superconducting transition temperature, it can expel the magnetic field. And that gives us the concept of the levitations. You might have heard that in Japan, like, there are the superconducting trackways where the train can move in a speed of 300 km/h. That's possible, like because they have minimized the resistance between this train's wheel and the track, because the track was made out of the superconducting material. And while they move in such a speed, they don't even contact with the substrate. They just float around. A concept called the levitation. Now, since the superconducting planes, like let's say, like the current flowing in this, in the circular orbit, current flows in a loop under the poles. Now you bring another magnet here. So superconductor can also flow the current. Supercurrent can flow also around the ring. So give a magnetic field B that never dies away. And it will repel the magnet as if there was an image magnet underneath. So if I have a superconducting plate here, and if you put a magnet on the top, so this superconductor will behave such a way that it will exert a force of this magnet, and the magnet will be moving up. Just like there is a magnet in the below. So there are repulsion between the same poles. It will behave like that way. So that's why you can see that this is a famous experiment, so this is the superconducting material, and which is made of the high temperature, high DC superconductor, and then there is a jar and there is a fish inside. You see that this fish is actually a dead fish. It was sitting here. Now it is floating. Similarly, this guy, this guy is a very heavy person. He is floating. He can float using a superconductor. He has 202 kilo ozone, sumo wrestler. But he can float using a superconductor. He can float in the sky until certain distance. Okay, so you have a class. So I think I have to stop it here. So you have also talk about the yogic flying. This is all possible of the superconductor. So today I discussed with you the preliminary concept of the three different things. One is the nanomaterials. Second thing is about this super cold atoms and quantum cryptography. And third thing is that about the superconductivity. These are all exotic phenomena about this quantum model physics. And the next class I will talk about another thing which have been possible in IIT Roorkee. That is the generation of the power from a very low cost material. So if you have questions, you can always ask me. And since this is an this class is not a typical course where you are teaching something or doing some mathematics. It is something to just to instigate your interest in particular area, and to so that you know also the different development in a particular field. So that's why I keep it very, very general. What are the interesting thing in this area? What the area people are doing in this area? So that's what about. So in the next class, I will talk you about this.
So good evening, everybody. I guess people will join as we start because time is precious for us and we have already waited for 10 minutes. So let me start. Okay. So friends, in the last class, we talked about technical writing as such. Technical writing, we tried to make sense of it. We tried to form an opinion about it. We tried to find out how is it different from writing we are familiar with. And at the outset, I made a distinction between creative writing and technical writing by putting it while creative writing thrives on the use of language and language play. So any story that can be narrated in 5 to 7 minutes might run into 500 to 700 page novel, and that will not at all be considered, a bad use of language. But if you had to read a technical report of 500 pages, certainly that will be a heck of a job and you would not like to go through that. So technical writing by its very nature has to be crisp, precise, concise, and to the point, to an extent that nobody, even if he or she tries, misunderstands it. And that is why we talked about the ways that can help us come out with a writing style which suits technical communication, which is precise, concise, direct, specific, and is not abstract, not ambiguous, not too elaborate. But by that, I don't mean that your writing should be curt. No, whatever has to be elaborated should be elaborated, but should not be elaborated beyond the required limit. So that is it. Like if you're talking about a scientific process, you talk about that process in no mean detail, but please ensure that your explanation is free from redundancy, equivocation, or ambiguity. And that is why the language has to be crisp, it has to be clear, and it has to be, appropriate. So we talked about this the other day, and I suggested how you have to take care of your sentences. Like the sentences should not be too small or too long. If, for example, if a sentence has more than 3 connectives, that will be considered long, and in that case, I would suggest you break the sentence into 2 for better clarity. The second thing, I also suggested that some of the words that sound unfamiliar, archaic, or difficult should be replaced by words and expressions that are in currency, that are familiar, that are easy to understand. I couple of such examples, like rather than writing accommodate, you can use fit. Rather than saying aggregate, you can use total. Rather than purchase, you can use buy. So these are some of the examples. Another way, you can make your writing direct and specific. So you may have seen this is considered archaic and literary, when people say that I would like to tender my resignation, no, I'd like to resign. So it's very simple and very straightforward. So this TION phrases should be replaced by direct verbs. So rather than saying kindly grant me permission, you can say kindly permit me. I would like to offer my suggestion. No, I'd like to suggest. So this is how you can make it straightforward. And again, regarding the uses of what we call cliché. Cliché are those expressions that have been overused out of their original context and as a result have lost their meaning altogether. You might come across several of them. Last but not the least, the iron hands of law, the burning question, the acid test, and so on and so forth. And we keep on using them even if they don't fit in. So overuse of such cliches should be avoided because that does not make your language look good. Another thing that you can avoid is jargons. Jargons are high sounding technical words and generally we use them as specialists. So when you are writing for the specialist, when one orthopedic surgeon is talking to another orthopedic surgeon, he or she might feel comfortable using jargons related to orthopedics. But when one orthopedic surgeon is talking to uh, uh, an eye surgeon, he should better avoid those specific jargons that are specific to orthopedics. And when a doctor is explaining some problem to people like us, the commoners, the laymen, his language should be that of common men, not a scientific term or terminology, because we would not understand that. So what we have seen, these are also trade secrets, and the doctors, well, they will always come up with some difficult, high sounding words to explain our simple problems. So supposing you have cough and cold, they'll say you're suffering from coryza or something, and you may be baffled. Am I suffering from some incurable disease? So they do that deliberately also at times, but then this is advisable on the part of the writer to make it a habit that the writing is free from such jargon so that even no specialist can understand that. Fine. So these were some of the things that we discussed, and I'll share the slides with you, and that way you will be in a better position to understand that. Well, friends, taking that discussion of writing skill forward, I'm going to talk about another key writing skill, writing of emails. Well, friends, we are living in an era where most of our written communication happens with the help of emails. And now there is a growing tendency to go paperless. And going paperless means this online communication will become the only means of communication in the coming days. And this is being done for two reasons. Obviously, for the ease of transmission, because in that case, we'll spare our valuable time from, packing it and spending money for sending it by post. The second thing is we have positive space. And that's why keeping the documents in a physical space is going to be difficult with the growing concerns and growing communication in the coming era. So if you go to any state office, let's say municipal office or so, sometimes you will feel mad if you are left in their, record room, because they have kept records of hundreds of years. Many of the files have been eaten by moths. Many of them have turned pale. Many of them have been have lost half of their writings. So they are in a very bad shape, and again, you have to pay a handsome money to different people to get your file out of these thousands of files. And I salute those babus and PNs who can even find out the relevant files after getting some bribe from you from the pile of those files. So hats off to them. But you may be aware that most of the organizations like ours now, they are doing away with physical record keeping, and we are going digital, and we are storing everything maybe in cloud storage system or in physical systems on hard disks and different kinds of devices. So this will certainly save a lot of space, and again this can be kept for a greater period of time, although it comes with its own risks. Sometimes there is hard disk crash, sometimes there is something, but yeah, we have learned to find the backups as well. So if hard disk crashes, still our data is saved and it is retrieved from backup server and backup storage. So well, and especially your generation of people, I don't know if you have, any of you have ever written any physical letter. Have you written any physical letter to somebody other than emails? Any of you?
Yes, sir.
That's great.
Yes, sir, in the past.
Yeah, how did you send it? By post?
Yes, sir. Speed post.
In
Yes,
envelope, or do you also did you also use postcard or inland?
I've used both.
Inland letters?
Envelopes and postcards.
Inland letters, have you seen? Inland, have you seen? अंतरदेशीय जिसको बोलते हैं?
Yes, sir.
अंतरदेशीय कार्ड, वो हल्के आसमानी कलर का होता था. And
yes,
we also had the facility to send it by air mail. So we used to send it to other countries as well. I wish I could have taken this out of my inventory to show you, because I sent such letters not only in India but abroad as well. And this is the one that I received from a professor from Cambridge, and that was long back in 1992-93. See, this is, he has written Inde, not India. Can you see this? And
No,
there
sir.
are, see.
सर हम भी लिखते बट हमारे बाहर दोस्त नहीं है.
This is by somebody from Jesus College, Cambridge. It was Professor Heath, whom I had written. I was a student at that point in time. So I had written to him because I wanted to do some research under him. So unfortunately, that could not materialize at that point in time. But then he sent me this beautiful letter, which I have still kept with me. Okay. This letter is dating 1997. Can you see that? Is it visible?
Yes, sir.
Yeah. So this is 18th July 1997. So I wish I could have, Anyway, so friends, writing emails is so pervasive that we all believe it comes to us naturally. As I said earlier as well, communication also comes to us naturally, unless we are doing it as part of our profession. But the moment we do it as part of our profession, we start feeling alerted. Why? Because the small mistake might lead to a huge loss. Loss of face, loss of opportunity, loss of job. Well, so that's why we have to be very, very careful. Writing emails to friends is different, and writing emails as part of profession is different. So whenever you are writing or you are responding to some professional emails, they have to be very cautiously worded. Well, you cannot send emojis just the way you send it to your friends without inviting some kind of trouble or some kind of misinterpretation. So, writing to your friend is always easier, but writing it as part of your profession, even that email also has certain degree of formality. Although email communication is considered to be informal. Fine. So friends, let's talk about it with the help of this presentation. It has 59 slides, but we'll just brush through and we'll just discuss the important points. So don't worry if you see too many slides. It is being shared. Sometimes my system gets hang. I don't know. Please let me know the moment you are able to see.
Sir, we are able to see it.
But then the thing is, how should I move it if I am not able to see it moving? That is the problem. Again, see, it is hanged. Wait for the program to respond, but it will not respond. So what do? I may have to close the program and get back to you again. Okay, am I audible? Am I audible?
Yes, sir, you are.
Yes.
Yeah, just wait. There was some issue. I'm just trying to. Is it shared now? Can you see my slide?
No.
Nothing, sir. Only.
Not
Nothing.
shared.
No, sir.
It says it has been shared. Now?
No, sir.
So I believe I have I joined two different windows or what?
Now it's visible, sir.
So we can see it now. We can see it.
Okay. So email etiquette, keeping your foot out of your virtual mouth. So that means you have to be very, very careful. First of all, how is it spelled? What do you think? Which one is correct? First one, second one, third one. I mean, there are so many variations. Can you tell me? Because we keep on using a couple of such varieties.
Fifth one.
Fifth one, E-mail. You mean this one?
Last one.
Yes, sir.
Last one. Okay, so let's find out. Craig, Microsoft and AP, they use E-mail with both small. Wired uses email without hyphen. And Email Experience Council says email is standard. That is without hyphen. Okay. But I guess we can use the first variety as well. So we can use both.
Then, sir, why email experience uses a capital E?
Now, this is also acceptable only. Okay. Let's see. In this one also it is written with E capital. Fine. So we come to a conclusion that we can write it in any way. Fine. But after hyphen, we never use capital letter. It should be small letter only. Fine. So initial E may be capital. And then if you are putting hyphen, it should be M small AIL. That is. Now the thing is, as we are growing used to using email as a means of communication and transmission of message, in the process we also find that email etiquette is also evolving. Anything which starts for the first time is not really known how would it go about. But as we grow, we evolve and we also give good thought to it, and accordingly we develop certain etiquette. Now etiquette शिष्टाचार जिसको बोलते हैं, तो आपने देखा होगा कि कहीं भी सबसे ज्यादा जो हम लोगों को परेशानी होती है वो इसी शिष्टाचार को लेके होती है। अब आपके क्लास में टीचर जाता है, अब खड़े नहीं होते हैं तो किसी किसी टीचर को बुरा लग जाता है। क्यों? वो कहते हैं कि आपने क्लास एटिकेट का पालन नहीं किया। अगर कोई टीचर क्लास ले रहा हो और आप बिना पूछे क्लास में घुस जाते हैं, लेट आते हैं, again the teacher will feel it bad. Why? You did not follow the class etiquette. Fine. If the teacher is talking about something and without any request, you straight away asked a question or stopped the teacher or halted his flow, that will also not be considered a good etiquette. So there are etiquettes everywhere. So you will find it everywhere in all the gatherings. When we go for any marriage party or any party, we do not straight away head towards the food stalls and start plundering whatever comes our way. Rather, we wait for a signal for the right time for the people to start, and then after we start it. So etiquette is followed everywhere, and social life is all about etiquette. So if we live in society, the society decides the etiquette for doing a lot of things. Fine. So that's why email etiquette is also evolving with the evolution of email as one of the preferred means of message transmission. So, well, we all know that now it has quickly become a communication standard and is internet's most popular application. And so we find an ever rising number in its user and the rate of usage. And as a result, we have seen how the mobile companies and other service providers have started talking about giving us more and more data. I remember in early days there was no talk of data because the mobile was only used for talk time. But now we are less concerned with the talk time and more concerned about the data because we are making use of internet. So right now, where are we? I mean, have we really understood email as a medium of transmission? Do we use it rightly or wrongly? So O'Connor and Tillman, they say that right now online writing is pretty much in its wild west stage, a free for all with everybody shooting from the hip and no serif in sight. That means all of us are writing, but none of us really knows how to create impact out of it, how to make its right use. So you are shooting without any sight or any target in your sight. So what do? So if you are serif, what should you do? Well, you will talk about certain rules. What makes email different? Email, you don't know who is writing it. So you can look at it. It may be communicated by a beast or our, beloved pet. Who knows? We can teach them writing and reading, and they can also send emails. Or maybe your system may be on and they will just come and press any button and it will be sent. So internet does not know. On internet we don't know who is sending emails, who is at the other end, and that's why it makes all the difference. Well, when we are talking to each other face to face, our non-verbal cues play an important role. We have already discussed that more than 90% is coming from non-verbal signals, and that's why it's so important. But in online mode, in online transmission, in writing emails, these non-verbal cues are missing the way they are used in face-to-face communication. Although some of it will be used, like tone, ambience, the mood, these things would be communicated through language. So non-verbal cues account for 65 to 93% of messages, And this includes only words. Okay, only words, and rest is cues, the bodily cues. So words are only 7%. So we can just understand we are handicapped while using email as a means of communication, because we are just using words, and so non-verbal is missing, and that is why our job becomes even tougher. So if there are no non-verbal cues in email writing, as I said, tone becomes very, very crucial, which is part of non-verbal communication. So in which tone am I writing? Is it sad? Is it bubbly? It is humorous? Is it serious? Is it angry? Is it endearing? Is it complaining? So tone becomes very, very important. In Germany and Britain, 23 and 14% respectively, a survey was conducted by Daily Mail, and 23 and 14% of respondents admitted that they have faced confrontations with their colleagues because their emails were misunderstood. So such cases are very, very common, and they become like that because of wrong tone. So if you're writing some serious messages in a humorous tone, people will not get the actual intent of the message, and that is why it is so important. Tone is so important. So if you're angry, your tone should be angry. If you are friendly, your tone should be friendly. And this you can do by using right kind of language. Now, messages meant to express mild displeasure can come across as tirades. Sometimes, you don't intend to hurt somebody, but such is the language, insensitive use of language, that it hurts somebody beyond expectation. So let me give you one example. In our institute, what happens whenever some student fails to submit the required document or fee within the stipulated time by the institute, they immediately send a message: your name has been struck off the rolls. Now, this may be a routine affair for them, and they might not realize what have they written. So recently it happened with half a dozen students, PhD students from our department, and one of these students happened to be my student. And immediately after getting this kind of message, the student started crying, and he called me late in the night. Sir, my name has been struck off the rolls. Now what do I do? Have I been expelled? Sir, my future is completely dark. I don't know what to do. And that student, I know, is a very meritorious student. He is from economically weaker section of the society, and even he was not able to manage his first semester fee, and for that he had to borrow from his mentor, some mentor. And and after joining here, he was supposed to get 31,000 to be precise, of fellowship, and he thought he will pay back his debt, and again he will save money to send back to home as well, and lot of dreams. The moment he came across this message, it was disastrous on him. And then I immediately realized, and I told him, this is a routine affair. Nothing will happen. Don't worry. You arrange your document and we'll send it, and we'll send a mercy appeal, and this will be revoked. And exactly it happens the same way. But then the candidate did not know. So see, the communication from our academic office is one of the examples of how a small communication can be disastrous. Some of the people, if they are too sensitive, might take some extreme step, that now that my career is completely ruined, what is there to leave? Fine. So, I mean, instead of that, if they can come up with something which is less harsh, but then they don't do that immediately. Before that, they send couple of reminders that if you don't do this, if you don't do this, if you don't submit it by this date, your name will be struck off. So if we look at that message in that perspective, we would realize that we are also at fault. So if you don't know how to carefully word your email, maybe your subtle criticism might turn out to be very harsh on the other person. Look at this example of tone. Well, this message is sent to female employees by H. Honcho, and it is regarding dress code. And look at this message. Clients will be visiting next week. Halter tops and jeans will not make the right impression. It's time you started dressing for the office instead of the beach. Leave your flip-flops at home. Now, if you get this kind of a message and you are a female employee, immediately you will sit on dharna that arrest this man. He has made indecent remarks against us. Fine. So even if you have to impress upon the people or the employees of your company that some clients are visiting next week and they are expected to make the right impression, so they are all of them are advised to come suitably dressed. That could have been quite proper, but not this one. So look at example number 2. Now this is still better. Reminder about what to wear to work. And this is addressed to all staff rather than female staff. So there is no discrimination as such. And look at the message which is written so differently that it does not hurt. So during the summer, our dress code is business casual. We think business casual means clothes that feel comfortable and look professional. Men, women, khaki pants. Men, khaki pants, leather shoes. Women, casual pants and skirts, leather or fabric shoes. Now, this looks like a professional message. Fine. Where you are not hurting anybody and you are putting your point across. So if you want your email message to be understood properly and not to hurt somebody, then avoid terseness in your message, which can be misinterpreted. Use face-to-face kind of communication if issue is sensitive, the way you can talk to somebody. Same may be delivered through your email. Read your emails aloud, looking for ambiguity, and if you think that there is any word or expression that is ambiguous, you can do away with that. Now, if you have to use smiley, what do you do? Rob Glaser asked to meet with Bill Gates, and Gates said no in a cold and flip email. Glaser denounced Microsoft at antitrust hearings. Well, so if you are cold and that kind of response will always be taken, not taken in the right spirit. So you can use humor, but humor is riskier. Why? Because there are many people who don't understand humor. And if people don't understand humor, then it will lead to rumor. So that is why this is so important. You can use humor, but still, nearly a quarter of employees have suffered problems with colleagues or clients because their use of humor in an email has not been understood or appreciated, according to a survey. And that is why using humor in your email, professional email, may be risky. So, participants in recent studies were able to accurately communicate humor and sarcasm in how many percent of emails they sent? According to Louis Dobson, 56% of the emails. Fine. So it is more than 50%. So there are more than 50% chances of your humor and sarcasm getting misunderstood. And that is why it is recommended that in a serious professional email, you be to the point and be professional. Don't be too personal. Well, if in doubt, don't send it. So Chevron was forced to pay 2.2 million to settle a harassment case based in part on emails with such subjects as why beer is better than women. Well, look at it. If the subject line is like this, even if you have written something else, well, you can be sued in the court of law and you will end up paying your lifetime earning to settle that. So always reread for ambiguities. If there are chances of getting misunderstood, don't use that kind of tagline. Signal the joke. If you have to use it, you can use one emoticon of green per email, and that is enough, not more than that. So if you ignore these rules, the great list guru will expel you into the gloomy dimension without email, and your days will be long and lonely after you have made a permanent impression in print for many to keep and repeat forever. And then one emoji. Well, this shows that the serious message has been sent in a humorous vein. And where is the catch? The catch is here, where the green emoticon has been used. Otherwise, this whole message till this point looks very, very serious. That if you don't abide by these rules, you will be expelled from the institution. And just think, what would you do without a job? Fine. There are different levels of formality when we are talking to people. Most of us view email as more formal than a phone call and less formal than a formal letter. Fine. So look at this request, meeting request, which is informal. Informal meeting request just has a subject line meeting, and it has a personal kind of tone. We need to set up a meeting between Jim, you and I. Can you arrange? I'm free next week. Thanks. We can look at the use of language, which is using the email a specific language, not the proper language. But it can be more formal like this, where you have the subject line reading meeting on FY86 planning 2 p.m. 12 itna. There will be a meeting of the FY86 planning task force in conference room 1 on December 28, 1984 at 2 p.m. The agenda for the meeting is topic is given, presenters are given, and time is given. So even in the formal, even if you are using email and you are using it for formal purpose, it will not be much different from the physical letter, except that it will not be having the address and salutation at the bottom. The spelling still counts, because if the spelling is wrong, it will create lot of problem in understanding. I can beat almost anyone's price and almost promise you success, and if I don't reach it, we won't charge you after the time we say we can achieve it until we do. Now you can find several such inconsistencies anyone's owned. So you will find several such inconsistencies of language in this communication. Proposal, you can see what is written. Proposal. So this kind of spelling error will create a very bad impression. And sloppiness is one of the 7 deadly sins, email sins. Bad grammar, misspelling, disconnected arguments. Well, 81% of the survey samples, indicate that they create negative feelings towards the senders. 41% of senior managers said badly worded emails implied laziness and even amount to disrespect. So that is why it is so important for you to be aware of these email etiquettes, which come closer to physical letters when it comes to the use of spelling, grammar, tone, punctuation, etc. So whenever you are in doubt, you always are on the side of formality. So many a time, people think, should I write dear sir, or should I write Mr. So and so and start? If you are in doubt, better to use more formality. Fine, rather than using less formality. So rather than starting your email with Mr. So and so, if you can write dear so and so, that will be preferable. Usually the problem is that we treat email too much like a phone call and not enough like a letter. But then this is not the case. Email is also a letter, not by post, but by sent online. So you can be conversational. An overly formal email message alienates the reader. And don't adopt a cold, remote, or superior tone in an attempt to sound professional. So, if you go to bigger organizations, you will find that even the bosses, superiors, they also write emails that have an undertone of conversational tone. So as if they are talking to you and they are giving you full respect, and they're talking as if they are your friends. So less, formal, emails are preferable to strictly formal ones. So questions to which answers are evolving is, do I need a subject line? Should I email a thank you note after a job interview? Should I communicate bad news via email? These are some of the questions that come to our mind. Hit send and it's gone. In electronic communication, people always say that you may have heard it a couple of times. कि तीर कमान से और बात जुबान से निकल जाते हैं तो वापस नहीं मुड़ते. What does it mean? It means that once you press the button send, your message is sent and you cannot, there is no way you can take it back. Fine. And that is why it is so important. And the second kind of mistake I have also made couple of times, and I was scolded by our director. At that point in time, I was the head of the department. When I was supposed to just reply to the director or any one individual, I hit reply all and the message went to everybody. And as a result, the director was displeased. Why did you send it to everybody when it was just meant for me and it was meant to be confidential? So always be conscious. Don't ever hit reply all without giving some thought. When you are not supposed to send it to everybody, don't hit reply all. Otherwise, it will ruin your career. And believe that deleted emails live on because they are still there in the database. And also know that your messages can be forwarded to any number of people. So if you make one mistake and you believe that you are sending it to one individual, that individual can forward it to hundreds, thousands of people. Okay, and he or she would not take your permission or consent for that. Colonel David Russell's rule is never say anything in electronic message that you would not want appearing and attributed to you in tomorrow morning's front page headline in the New York Times. So friends, that is the problem. Once it gets out of your hand, it goes out forever and can create a huge uproar and can damage you without proportion. So you need to understand that. And that is why don't be in a hurry and don't send anything that you don't want to appear in the newspaper attributed to you that you made this kind of a statement. And mind it, email is never private. Even if you are sending it to some individual, it is not completely private. Pillsbury assured employees that emails were private. And many a time it happens, organizations say that, the emails sent within the organization are private, but then this does not happen. Michael Smith was fired after sending an email calling his bosses backstabbing bastards, believing that his email is private and he would not be caught. A court held that he had no reasonable expectation of privacy, and so he was fired. So emails can be tricky. Don't send emails that have any kind of wrong message. There are three manners or mavens. See, typing in all capitals in electronic communication means nothing special. Typing in all caps is normal. The second says you are shouting. The third says it's okay to forward this message to others. The fourth says this message is very important. So it's not that, in the email world, anything goes unnoticed. It's like the political world. If Rahul Gandhi smiles at, Modi, people will certainly find some meaning. It cannot be an innocent smile without any purpose. No. So in your electronic communication also, if you are typing in all capital, that will have some meaning. So typing in all capital means you are shouting. It is equivalent to shouting. So only type in all caps if you really mean to shout. Otherwise, don't do it. Again, emails very structure encourages curtness. Okay, curtness means something which is very curt. It does not follow any kind of etiquette. Just one. Yes, so there are chances that you might create some kind of mistake. Like if you leave the subject line blank, you know, that will certainly be considered curt. The to and from fields seem to make salutations and signatures, but then they are redundant or unnecessary because our emails are not like that. In emails, we put the email IDs of people, and that is about 2. And the from signature is, all of us have configured these signatures in our system, so they automatically get attached to our email. What we have here is the ideal breeding ground for rudeness. So if you don't put a subject line, and if you don't put a salutation, that means you are sounding rude. Let us look at this. What is this? See the subject line says nothing important. What is it? And to entire address book. What is this? And look at this. So-called service at your crummy excuse for a store today. Now this is also not okay. Again, you need to use BCC wisely. And BCC, we put those email addresses to whom we copy the message, but we don't want the receiver to know about it. Who other people have been sent the same message. If you are furious and must answer an email right away, leave the address line blank. Because if you hit send, it will not go. It will again come back to you. And it will say that there is no subject line. Would you like to send it anyway? And that instant will give you some time to reflect back on it and cool down in the process. And so maybe you might like to put an address line, subject line, and then send it. Fine. I mean, you would like to put the address and then send it. Would you open mail from this kind of, emails? Whenever we find such emails, we always doubt them. Email recipients put more weight on who the email is from than any other item when choosing. And accordingly, they decide which emails to open, which to delete, which to complain about. So be complete and be recognized. Most of the phishing emails are sent by people in the name of somebody else. So couple of times it has happened that, in my name. Somebody made a fake ID and they sent it to all my colleagues and students and contacts that I need money and so on and so forth. And the moment I came across, I issued a disclaimer that this is a phishing mail and don't reply to this. So, this is really important. I appreciate recently I announced a fundraising campaign to help one of your seniors who needs a kidney transplant, because I am also the chairperson of Institute Medical Emergency Fund. And immediately one of you from your class sent an email to me to confirm whether this is a genuine email sent by me or somebody else. And when I confirmed it, he immediately contributed and sent me this confirmation. So while I expressed my gratitude to him for contributing for such a good cause, I also appreciate his sharpness of mind, that before sending money, since it involves money, it would be pertinent on my part to talk to sir and find out whether this is genuine or not. So let us quickly look at the rest. So your subject line should be, answering this question: what your email is all about, and why somebody should read it, and what is in for him, or what am I being asked to do. So that's why you can look at it. The subject line says change of plans. Now change of plans immediately tells us about some plan that we made. Marketing meeting rescheduled. You can look at it for so and so. So immediately by looking at your subject line, people will get it. Look at this as well. EOM, end of message. So lead with the main idea. Browsers may not display more than first 25-35 characters. So create single subject message. Message should not be too long. Keep track of threads like first year communication skills. Was first year communication skills? Well, keep track of it, and future communication will appear in this. Before you type anything into a new message, have explicit answers to two questions. Why am I writing this? And what exactly do I want the result of this message to be? Before you hit send, review and delete. Negative comments about management, criticism of staff or performance issues, bonuses on salary issues, product or liability issues, gossip, humor or other ambiguities. You look for them, and if they are there in your body, please do away with them and clean your message. Right, so emails are easy to read. Make paragraphs 7-8 lines, insert a blank line between paragraphs, use headlines, bullets, numbers, avoid all caps, that's outing. As I said, if a message is longer than 3 screens, send an attachment. So look at this noise level in the break rooms. How can we satisfy everyone? Your ideas are welcome. Like our work clothes, the preferred writing style has become business casual. So avoid extremes, not too pompous, not too passive, not too careless. It should be something like a golden mean between formal and informal. Do I need a greeting? Consensus is yes, otherwise you can seem unfriendly. Consensus is match greeting in tone. Formal, sincerely, best regards, cordially. Informal, thanks, all the best, talk to you later. Use this signature line that gives your name, title and contact information. As I said, 36% of employers on Monster prefer thank you notes sent by email, and 29% prefer traditional letters. So what do we understand by netiquette? It is net plus etiquette, and the electronic equivalent of a set of fuzzy rules that tell you which fork to use with the salad course. Netiquette does not consist of a set of rigid rules, however, and it encourages you to adopt a certain attitude of thoughtfulness. That's it, but then is not too rigid. And this is the available resource that you can look for, and this is all about it. Thank you so much. I understand that we started a little late, and that was the reason our class has overshoot by 15 minutes or so. But then we had to complete this topic, and we have completed it. Okay, fine. So if you have any queries, you can quickly ask me, or you can email me your queries later. Do you have any queries? Yeah, please.
Sir, please share the slide.
I'll share this slide. I'll share the previous slide as well. Okay, anything else? Okay, fine then. We are winding up. Thank you very much.
Thank you, sir. Have a nice time, sir.
Thank you, sir.
Thanks a lot, sir.